Good morning. My name is Shobha from BSC Chemistry Honors first year. Today I am going to prepare a video for audio video impaired students. My topic is Unit 2 Phenols. Objective Objective of this unit are to study the structure and bonding of phenol, to study physical and chemical properties of phenols, their acidic characters. Beside these objectives, this unit will make aware the students about general method of preparation of phenols, comparative acidic characters with alcohols, various chemical reactions. Introduction. Phenols are compound in which OH group is directly attached to an aromatic carbon like benzene ring, although they share same functional group with alcohols where the OH group is attached to an aliphatic carbon. The chemistry of phenols is very different from that of alcohol. The simplest phenol is hydroxybenzene called phenol, which formula C6H5OH. Simple phenol is an antiseptic. A phenolic compound, hexachlorophene, is a constituent of several mouth washes, deodorant, soaps, and medicinal skin cleaners. The OH group consists of an oxygen atom bonded to sp3 hybridized aromatic carbon and H atom via sigma bond as follows. Both carbon oxygen and oxygen hydrogen are polar due to the high electronegativity of oxygen. Conjugation exists between an unshared electron pair of oxygen and aromatic ring. This results in comparison with simple alcohols, a shorter carbon oxygen bond distance, a more basic hydroxyl group, a more acidic hydroxyl proton. Electronic structure of phenol can be represented by resonance hybrid of the following canonical forms. It must be noted that the aromatic compounds of OH group is not directly attached to benzene ring are not phenols but are called aromatic alcohols. These may be regarded as aryl derivatives of aliphatic alcohols. Nomenclature. Functional group suffix common phenol, systematic benzol, functional group prefix hydroxy. The hydroxy derivatives of toluene has been given in named crisols. If a phenolic moiety is included in the molecule which is named as IUPAC system, OH group is specified as a substituent according to the order of precedence. In such a case of substituent, COOH and CHO is assigned number 1. The systematic and common names of some phenols have been illustrated below. Monohydric phenols, phenol, 2-methyl phenols, 3-methylphenol and 4-methylphenol, 2-chlorophenol, 2-hydroxybenzaldehyde, 3-hydroxybenzaldehyde. Method of preparation of phenols. There are many methods which are used to prepare phenols from aryl sulfonic acid. An aryl sulfonic acid gives the corresponding phenol or heating it with molten sodium hydroxide at 560 to 620 Kelvin. The sodium salt obtained is hydrolyzed with acid to obtain free phenol. From haloarenes, chlorobenzene is hydrolyzed by heating it with 10% NaOH at 623 Kelvin and 320 atmospheric pressure in presence of Cu catalyst. Phenol is obtained by acidification of sodium phenoxide. Hydrolysis diazonium salts. A diazonium salt is formed by treating an aromatic primary amine with nitrous acid at low temperature 273 Kelvin and 278 Kelvin. Diazonium salt are hydrolyzed to phenol reacting with dilute acid. Decarboxylation or phenolic acids. Phenolic acids upon distillation of soda lime and decarboxylated to form sodium phenoxide which upon hydrolysis give phenols. Oxidation of Grignard reagent followed by the hydrolysis aromatic Grignard reagent on treated with O2 in the presence of light followed by hydrolysis in presence of mineral acid give phenols. Commercial preparation of phenols. Phenols are important class of compounds used commercially for many purpose. Acne needy commercial synthesis is pilot scale. Still, some amount of phenol are obtained from the coal tar However, about 90% are produced synthetically in industries. From coal tar, generally heavy or middle oil containing phenol and naphthalene in crude oil are subjected to extra cooling. As a result of naphthalene crystals are separated and allowed removed by filtration. The remaining fraction is treated with NaOH with dissolve the phenol by making phenoxides. Ultimately, carbon dioxide gas is blown through the solution in order to liberate phenol. The water layer containing Na2CO3 is drawn off, leaving crude phenol behind, which is fractional to recover the individual phenol as follows. From cumene, commercially, phenol can be synthesized from cumene, which is turned in prepared from petroleum using Friedel-Crafts reaction. The cumene obtained from petroleum is as above to oxidized as 130 degrees Celsius in presence of metal catalyst, which give phenol as the ultimate product of involving the intermediate compound in sequence as follow. Physical properties of phenols. Phenol has higher boiling point than arenes and haloarenes and ethers of same molecular weight. It is due to formation of intermolecular H bond. Pure phenol is white crystalline solid. Smelling is disinfectant. It has to be handled with great care because it causes immediate white blistering to skin. The crystals are often rather wet and discolored. Phenols are springly soluble in water but readily soluble in organic solvents such as alcohol and ether. The boiling point of phenol increases with increase in number of carbon atoms. The OH group in alcohols and phenols is involved in intermolecular hydrogen bonding, which is responsible for higher boiling point that is lacking in ethers and hydrocarbons. Acidic character of phenols. Unlike alcohols, phenol is strong acid. Phenols turn blue litmus into red and react with metals, liberating hydrogen. Phenols behave as acid because of presence of more polar OH group in them. They ionize in aqueous solutions to give H positive ion to a base. However, they do not react with carbonates or bicarbonates. The greater activity or acidity of phenols can be attributed by the resonance stabilization of phenoxide ion formed after losing hydrogen ion. The delocalization of the negative charge over the benzene ring stabilizes phenoxide ion. No such stabilization is possible in case of alkoxide ion. Phenol is very weak acid than carboxylic acid and position of equilibrium lies well to the left. Phenol as well as phenoxide ion both are resonance stabilized. Negative charge on oxygen atom is delocalized around the ring. The benzene ring helps to stabilize a negative charge on phenoxide ion. This makes phenols appreciably acidic. The more stable of ion, the more likely is to form. Phenol react with the aqueous sodium hydroxide solution to give a colorless solution containing sodium phenoxide. The various contributing structure of phenol and phenoxide ion are given below. Comparative acidic character of alcohol and phenol. The ionization of alcohol and phenol take place down in equation. Ionization of alcohol in alkoxide ion, ionization of phenol in phenoxide ion. The alkoxide ion negative charge is localized on hydrogen, while phenoxide ion the charge is localized. The localization of negative charge makes phenoxide ion more positive and favors the ionization of phenol. The hydroxyl group in phenol is directly attached to sp2 hybridized carbon of benzene ring, which act as an electron withdrawing group. Due to this, charge distribution of a phenol molecule as dissipated in its resonance structure case the oxygen of OH group to be positive. A compound in which the hydroxyl group is attached to an aromatic ring is more acidic than one which hydroxyl group is attached to alkyl group. Acid react with the more reactive metals to give hydrogen gas. Alcohol and phenol react with atom reactive metals like sodium, potassium, aluminium, liberate hydrogen gas. The reaction of phenols with metals as well as NaOH indicate it is relatively more acidic than alcohol and also water. The sp2 carbon of phenol attached to O being more electronegative than sp3 carbon of alcohol is decreased the electron density of oxygen. Because of this, oxygen overlaps still more electron seeking character and releases a proton by taking the shared pair of electrons with it. Effect of substituent on acidity of phenols. In substituted phenols, the presence of electron withdrawing groups such as nitro group enhance acidic strength of phenol. It is more pronounced when such a group is present at ortho and para positions due to the effective delocalization of negative charge in phenoxide ion. On the other hand, electron releasing groups such as alcohol in general do not favor the formation of phenoxide ion, resulting in decrease in acid strength crystals, for example, less acidic than phenol. Electron releasing group like alkyl group increase the electron density on oxygen and decrease the polarity of OH bond. This decreases the acidic strength and hence alkyl phenol have greater pKa value as compared to phenol itself. On the other hand, electron withdrawing substituent increase the acidity and phenol having these substituents has a lower pKa value than phenol. In fact, 2,4-dinitrophenol and picric acid is more acidic than many carboxylic acid. Chemical reaction of phenols, alcohol and phenols both contain OH group attached to carbon, but in case of phenols, the carbon atom is a member of phenyl ring is also shown above in resonating structure in phenols. Carbon oxygen bond acquires double bond character because of delocalization of electrons from oxygen to phenyl ring. In results, the carbon-oxygen stronger and OH sigma bond increase electron density in phenyl ring activities aids and give electrophilic substitution reaction. Alcohols, no resonance is possible. Not bonded electron pair remain localized on oxygen atom. The carbon-oxygen linkage thus retains its sigma character and weak as compared to than in phenol. Phenol undergo two types of reactions: reaction involving OH group and reaction involving aromatic ring. First, reaction involving OH group. Acidic character. Phenol are acidic compared to alcohol as they furnish proton to form alkoxide in which stabilization of resonance acidity of phenol is less than carboxylic acid. Phenols, when react with aqueous NaOH or KOH to form soluble sodium salt known as phenoxides. Reaction with FeCl3 phenoxide grieve colored complex when treated with ferric neutral chloride. Replacement of OH when distilled with zinc dust, OH group is released by oxygen atom. Replacement of OH by halogen. Unlike alcohols, OH group cannot be replaced by alkyl halide. However, halogen derivative are obtained by treating with PBr3 and PCl5. Replacement by NH2 function OH plus NH3 in the presence of ZnCl2 at 300 degrees Celsius gives amines. Ether formation. The sodium phenoxide of phenol undergoes Williamson synthesis and react with alkyl halide to give ether. Unlike alcohols, phenols also react with diazomethane and DMSO. Phenols cannot be esterified directly by using carboxylic acid in the presence of mineral acid. This is because less nucleophilic oxygen of phenol compared to alcohols. B. Organic reactions involving aromatic ring. The aromatic ring of phenol generally undergo electrophilic substitution reaction in which the hydroxyl group is a powerful activating group and hence phenols readily undergo electrophilic substitution reaction. Phenol is more reactive than benzene towards electrophilic reagents because there is an interaction between the lone pair of oxygen atom in OH and oxygen and the ring. When increase the availability of electron in aromatic ring, also it directs the incoming group to ortho and para position in the ring. These positions become electron rich due to resonance effect caused by OH group. In this reaction, electrophile attack the benzene ring and replace one of its hydrogen atom. Since ortho and para positions of phenols are electron rich, substitution takes place at this size. Common electrophilic substitution reaction take place in phenols are as follows: halogenation. The OH group is phenol can be donated electron back to the delocalized pi system, helping to stabilize the intermediate of electrophilic substitution, so making phenol much more reactive than benzene. It will react immediately with bromine water, decolorizing it and forming a white precipitate of 2,4,3 tribromophenol. If bromine water is added to solution of phenol in water, the bromine water is delocalized and white precipitate is formed. The usual halogenation of benzene takes place in the presence of Lewis acid such as FeBr3, which polarizes of halogen molecule. The faster reaction in water is due to the presence of phenoxide ion. In case of phenol, the polarization of a bromine molecule takes place even in the absence of Lewis acid. It is due to the highly activating effect of OH group attached to the benzene ring. Chlorine in the absence of solvent gives 2,4-chlorophenol. Bromine in a non-polar solvent CS2 and carbon tetrachloride gives 2,4-bromophenol. Bromination can be limited to monobromination to give mainly 4-bromophenol using low temperature and less polar solvents such as sodium disulfide. Other product form in minor quantity is 2-bromophenol. Nitration of phenol. Phenol can be nitrated with dilute nitric acid. A monosubstituted compound is obtained with dilute nitric acid at room temperature. Phenol reacts with dilute nitric acid at room temperature to give a mixture of 2 nitrophenol and 4 nitrophenol. When concentrated nitric acid tri-substituted product 2,4,6 trinitropicric acid is obtained. Acylation and carboxylation ester of phenols are obtained on treatment with anhydrous aluminum chloride, which further treated with Lewis acid AlCl3 yields ketone of phenols. Fries arrangement. Kolbe's reaction on reaction sodium salt of phenol with carbon dioxide orthohydroxybenzoic acid is formed as main product. The temperature is 400 degrees Kelvin and a pressure of 4 to 7 atm is required. Sodium salicylates formed which an acidification yields salicylic acid. Frey's rearrangement enables the preparation of acyl phenols. The reaction of catalyzed by Bronsted or Lewis acid. The acids are used in excess of a stoichiometric amount, especially Lewis acid, since they form complexes with both the starting material and product. The reaction of orthopara selective so that, for example, the site of acylation can be regulated by the choice of temperature. Coupling reaction phenols and azo compounds by coupling with aryl diazonium salt in presence of alkali. Gatterman reaction introduction of CHO group ortho to OH group by treating with HCN HCl ZnCl2 catalyst is known as Gatterman reaction. This reaction is used to formalization of aromatic ring. Linders manage reactions when phenol is treated with 40% aqueous solution of formaldehyde in the presence of dilute acid or alkali at low temperature. A mixture of ortho and p-hydroxybenzyl alcohol is formed. This reaction is known as Linder-Mannes reaction. On heating, these compounds condense themselves to give linear polymers of elimination of water. This reaction are the basis of preparation of phenol formaldehyde resins. These materials were developed by Backland and hence bakelite. They are the thermoplastic solids soluble in many organic solvents when warmed with hexamethylene tetramine, which splits up formaldehyde and ammonia. Further, methylene brigades are formed and thus three-dimensional polymer results. Revertimer reaction. The process of formylation of phenols with chloroform in alkaline solution is called Revertimer reaction. Phenol react with chloroform in the presence of sodium hydroxide or potassium hydroxide solution followed by acidification of hydroxyaldehydes. Mechanism. Raymond-Taman reaction is an electrophilic substitution reaction. The first step is generation of electrophile, generation of dichlorocarbene, electrophilic substitution in phenol ring. Use of carbon tetrachloride in place of chloroform gives silicic acid. A mixture of ortho and para isomer is obtained in which the ortho isomer predominates due to more thermodynamical stability. If one of ortho position is occupied, the para isomer is the major product. When any sol is treated with chloroform in the presence of alkali, a commercially viable product, vanillin is formed as a major product. Haubin-Havesh reaction. Reactive polyhydric phenol in which OH group are meta to another may be acylated by treating with alkyl cyanide in the presence of certain Cl2 and HCl. This reaction is known as Haubin-Havesh reaction. The product of reaction is a phenolic ketone. Phenols do not respond to Hauben-Havesh reaction. Condensation with phthalic anhydride. Phenol when treated with phthalic anhydride in presence of H2SO4 gives phenol phthalate, a colorless compound which produce pink color with alkali solution due to the formation of colored sodium salt. It is a popular indicator used in acid-base titrations. Oxidation. Phenol is easily oxidized to p-benzoquinone and similarly hydroquinone on oxidation with silver salt gives p-benzoquinone. This reaction leads to the use of hydroquinone as a photographic developer. Under drastic condition upon oxidation, phenol gives tartaric acid, oxalic acid and carbonic oxide. Reduction. The OH group is stable and the catalytic reduction of phenol yields cyclohexanol. Substituted phenol would in same fashion form substituted cyclohexanol. Uses of phenols. Phenol in dilute solution was first successful antiseptic used by the Lister. Non-substituted phenol are used both as antiseptic and disinfectant, kill pathogens already which is present.